would like to thank you all for coming to join us today. Today we have Dr. Cameron Hurst, who is the Associate Professor of Biostatistics in the Data Management and Statistical Analysis Center, and also Clinical Biostatistician in the Clinical Epidemiology Unit and Academic Clinical Research Office at the Faculty of Medicine at Kent University. He obtained his PhD from Griffith University in Australia, and he has more than 50 publications over a range of areas of statistical application, and over the course of his career, he has been involved in many health research projects. Dr. Hurst has nearly 20 years' experience as an academic statistician with proficiency in the full range of biostatistics methods. He has developed innovative approaches to deal with analytical problems where existing methods fail. His main areas of research interest are statistical methods for high-throughput genomics and proteomics platforms, singular nucleotide polymorphism association studies involving large multi-SNP data sets, development of psychometric and clinical scales to the study of a number of diseases, and chronic disease epidemiology, especially type 2 diabetes mellitus. So please welcome Dr. Cameron Hurst.
Okay, thank you very much. So what I'm going to cover today, I'm going to have to cover quite a bit. Can everybody hear me? I'll just check I'm loud enough. I'm going to have to cover a lot of ground today. In the first session, I'm going to cover the R statistical software very, very quickly. And I have to apologise for that. So hopefully by the end of the afternoon, you'll have a basic understanding of R, and I'll sell R to you in a moment. But the main role of today's workshop is going to be in covering longitudinal, or I should say methods for longitudinal data analysis. So I'll just start with a little bit about me. Thank you for the introduction, Stephen, that's very good. I guess the short story is I've got about 20 years experience in the field of biostatistics and just consulting thousands of projects, way too many for me to count. And these range from preclinical studies all the way through to clinical and community-based, I should say, population-based epidemiological studies. I'm from Konkan. You can probably tell by my Isan accent that I have. My main role these days is advising or supervising PhD students, which makes me very happy. I don't have to do any undergraduate teaching anymore because it used to drive me crazy, absolutely crazy. So I'm very happy, and I love teaching audiences like this because you don't ask me, why do I have to do biostatistics? So I don't have to spend all of my time answering that question. So I do teach into courses like this quite a bit. I actually come from Queensland in Australia, which is the northeastern part of Australia, and I like to think of it as the Isan of Australia. Okay, so we're going to cover 4 sessions today, crammed right into one day. The first session, we're going to cover the basics of R, and as I said, very briefly. So we'll cover data input and output, basic data structures that R uses, some graphics, and very importantly, I will introduce modelling in R, because this is what we're going to be doing today, statistical modelling of longitudinal data. In the second session, I'm going to cover modelling continuous longitudinal outcomes. After lunch, I will talk about the same thing, but for categorical outcomes. And I'm really going to focus on the binary case, but the methods I will cover can really be used for any type of categorical outcome. Well, I shouldn't say any, but certainly Poisson, so count processes, and multinomial. A modification of the methods that we use. We could also consider ordinal outcomes as well. Really, we can consider it the same thing. Finally, this afternoon, we're going to have a hands-on session. So what I'm going to do for that, that's not structured at all. I'm really going to sit here with a data set and get you to follow me through an analysis. The reason I'm doing that is to get you used to coding in R. I understand most people use Stata, is that right? Or Stata, depending on what country you come from. Is that right? Anyone use anything else? Any SAS users? Good, SAS are horrible. You use SAS, do you? It drives me crazy. My first 8 years were in SAS. I used to think it was the best language in the world until I went to another language. It's unnecessarily cumbersome, and it's a wonderful package. It just always takes 10 years to get it to do something simple, and pages of code. You'll find R much more succinct, like Stata. Stata is very succinct too. So yeah, SAS is can be a little bit painful as a programming language, I found. It's a very old language. I think it was in the 60s, that language. I thought programming PL1, literally programming language 1 is the language used in SAS. Any SPSS users? Anyone willing to admit they use SPSS? I'm very happy to see that. It's a terrible, terrible package for biostatistics. Unless you want to do a t-test, of course. Okay? It's not for modelling. Not in biostatistics. Very good at some applications in psychology and social sciences, but that's what it's for. Statistics package for social sciences. Sorry, I shouldn't really be going on to software, but one of my missions in life is to eradicate SPSS from the field of biostatistics. Anyone who knows me knows that this is a standard little thing I say in practically every talk. Yeah, I think my last university forced me to teach in SPSS for 5 years or something like that, and now it's my turn to get my own back.
Well, I would say that your idea is similar to an adoption.
Is that right? That's good. That's exactly right. Yeah. No, that's right. I think we're professionals here. We shouldn't be using Mickey Mouse packages, and that's what SPSS is. It's really, it's sort of like using Excel for advanced modelling. You wouldn't do it. Okay. Okay, just some conventions I tend to follow. Good things to note will be in the green box. Common errors and pitfalls that you might come across are in the red box, and all of the important syntax. So I'll give you some syntax. That's not in a purple box, but the important stuff that you should come back to and remember will be in the purple box. Just before we start, and I think most of you will understand this quite well, using Stata and SAS, that when you cover a new package that's syntax-based, you're not expected to memorize it straight away. It's really through using it and coding using this package that you learn it. So the stuff I'm going to cover today, you don't have to remember it. You just need to remember it's in these notes, or that can do these things. And then you just go back to a reference manual or these notes or whatever to come back and So using syntax is the best way of learning it. So this session, I'm just going to talk a little bit about what R can do, where to get it, and I'll talk about RStudio, which is essentially nothing more than an integrated development environment. It's just something that sits over the top of R to make using R a little bit simpler. Only a little bit simpler. RStudio's a little bit of an illusion. It just makes it look a little bit more like Stata. It's really not much to it at all, but it helps a lot of people. Just makes things a little bit more convenient using R. But it's really just R put in the middle of a box with other boxes. That's all RStudio is. After I cover that, I'll go into data structures and data input-output. So some basic conventions used and data structures. Reading in data, which is a very important thing to learn how to do. And the idea of a data frame, which is R's data set, in other words. And then I'm going to talk about libraries. They're a very important feature of R. In fact, they're really R's strength above all of its competitors. Are these third-party libraries that anyone can write. Then I will talk about some basic statistics and plots, so R graphics, for univariate, bivariate, and then a very quick introduction to modelling. I'm going to give you an example using the general linear model, so linear regression in other words, and a generalised linear model. We'll just look at binary logistic regression. The funny thing about R is simple statistics are tricky and advanced statistics are very, very simple in R because it uses the idea of a model and they look very, very similar. It doesn't matter what model you use, the conventions are exactly the same. So modelling in R is very simple to do. It's doing t-tests and chi-square tests where they're not tied together through a model. There's no unifying theory that ties them together, so they have a different look and feel, these different tests. The models, unifying theory ties them together, so they all look the same. Finally, I'll talk about the getting help. This is actually one of the trickier parts of R, and I think it's getting the help that changes you from a rank amateur with R to really getting to the point where you can sustain yourself with this package. When I started it 10 years ago or so, you didn't have YouTube walkthroughs. They make life so much easier. There's a lot of stuff on YouTube, how to do this in R, how to do that in R. So you're very lucky in that respect. I learnt it, none of my colleagues used R at the time, so it took me months really to get up to speed with this package, but it's a lot easier now. Okay, so just starting with R, it's a pity it's not, it doesn't cost any money, because I'm sure I would get a commission on it, because I try to sell it all the time. It's free, okay? It doesn't cost anything. In fact, it's not only free, it's open source. What do I mean by that? Open source means the code that R is written with is freely available, so it can be freely extended, okay? Now, you're probably not going to do that. What's important for you is it's free. You can download it for free. It brings together the basic functionality that the creators of R, who have called the R core team, thought of. These are the absolute basic things: reading in data, basic data manipulation, basic statistical tests. So that's the first thing. And work from others, like you and me. Okay, so if I come up with a specialized method that can do something, I can actually upload that to R and other people have access to that. And that's what gives R its real strength. It can do anything. It's well ahead of any of its competitors, because as soon as a paper is published, that functionality is available. If I come up with a new test, it is there. With SAS, with Stata, it takes years for that to filter down and their programs to go through it and so on. So the actual developers of a lot of these statistical techniques are the people who actually upload it to R. R is also object-oriented. I don't want to go into too much detail about what that means. For you, what it really means is if we have a model, every model has a summary function. So if I want to summarize that model, I will just write summary, whatever the model is. So I name that model, and I ask for a summary of it, I ask for a plot of it, and so on. I'll talk about this a little bit more this afternoon when we get to it. Okay, I guess one point is any data we have, any analysis we have, any function we have, we give it a name. Cameron, for example. I'm calling this method Cameron. Cameron has a y variable, Cameron has an x variable, he has a plot, he has a summary, and so on. So that's the idea of an analysis, a data set, a function being an object. Okay, so what can R do? It can do the basics, and I'm not actually going to go through these tests at all, because most of these tests we can use a model to test a similar hypothesis anyway. But it can do the Pearson's correlation coefficient, independent and paired t-tests, chi-square tests of independence, and so on. As I said before, the classical bivariate tests are a little bit cumbersome. They're not tied together through unifying theory, so they all look different. R's real strength is in its modelling, when we have a y and some x's. So it's these intermediate to advanced methods that are the real strength. So it can conduct general linear models, generalized linear models, so logistic regression, Poisson regression, so on. The Cox proportional hazards regression and other survival analysis models, mixed and marginal models for correlated data. That's what we're doing today. So that's going to be linear mixed models, generalized linear mixed models, and generalized estimating equations. They're exactly what we're focusing on today. Just some other more advanced methods that it will do. Really, I shouldn't even be going here because it can do thousands and thousands and thousands of things. But I guess the more common ones that are used, generalized additive models. These are particularly popular these days in environmental epidemiology, where a lot of the time we might have seasonal or cyclical effects for temporal or spatial variation in a disease outcome. Multivariate methods, and I mean true multivariate methods, so multiple outcome variables, so factor analysis, principal component analysis, so on. Time series analysis methods, specialized analyses, like methods for high throughput data sets that we see in genetic and genomic studies these days. In fact, that's a very big area of our is in the genomics data analysis area. In terms of graphics, R also produces excellent publication quality graphics. Really, you can do anything in R, and it's actually, again, it's well put together. I just remember SAS when it came to graphics, whenever I wanted to do something. And SAS does anything you want to, but it's 3 or 4 pages of code just to get your graph exactly right in SAS. Where in R, you can do it in 2 or 3 lines. Yeah, that's right. So there's a large range of graphs available that really are off the shelf with R, but there's also millions of them that other people have done, and there's actually websites dedicated to all of these specialized graphs that people have developed, and they just give you the code. That's one of the beautiful things about R, because it's free. We have all of these people around the world who give freely of their time and give you their code to do things. So you don't have to sort of go and spend all of that time writing things from scratch. People just give it to you. As long as you don't charge money for it, that's the idea. So where do we get R? We don't really need to know this today because we've got it on the machines here. But you can just go to the CRAN repository to get R. It takes about 5 minutes to download. And this site will give you both the base package, which is the basic functionality, but also all of the contributed libraries. And there are thousands of third-party libraries available. You wouldn't download them all. It's also cross-platform, available on Windows, Linux/Unix, or Mac platforms. So when you open up, and this is what puts a lot of people off when it comes to R, you get a blank screen, okay? But you're not going to see that blank screen because we're not going to use R directly, we're going to use RStudio. But when people are faced with a prompt, the first time they open the package, a little cursor blinking there, now what? We can use R like a calculator. Well, I wouldn't do it, but if I want to, I could say into X, into the object I'm going to call X, put the value 1.3 into the object I'm going to call Y, put the value 2.5, add them together and see what you get. Now, I just want to point this out. There's something simple here I want to talk about. This is the simplest notion of it. That is an object, X. Into that object, I'm going to put the value 1.3. If I want to get that value again, I just type X at the prompt. Okay, that's the simplest idea of objects. Now, we're used to thinking about variables and values as objects. What we're not used to thinking about is analyses as objects. And I will come back to this topic in a minute. So, should I use R in that way? Should I just type things at the prompt? Definitely not. It's no way. For a start, we wouldn't be saving our code, and I would just have to remember things in my head about how to do things. So I don't want to type in my R line, hit enter, another line, hit enter. I want to collect it together into a script file, so into a syntax file. There's a number of editors around. TinR, Notepad++, which is a more generic one. You could use that for C if you want, or C++ programs. But the one we're going to actually cover is called RStudio. As the name suggests, it's especially for R. And we can download it from here. Okay, so when you get back onto your own machines, you can download R from here. Always do that first. Once you've got R on your machine, then go and download RStudio, okay? Because RStudio just sits over the top of R, and it's nothing special. It just makes it look a little bit better, a little bit more convenient to use. RStudio is also cross-platform, so it works in Windows, Linux, and Mac. So this is what RStudio looks like. Here's where we would type our syntax. So this is a syntax file. So it's just at the moment called untitled1.r. This is where I run the syntax. That's just R. That little box there is exactly what we saw before. That's R itself. Here, we'll just list what data sets are in memory and what other objects are in memory. They can be data sets, they can be analyses, they can be functions, and so on. And finally, this window here can be used for a couple of things. It can be used for help, it can be used for your plots, and so on. You'll get used to this a little bit more later. I know you're not going to remember that. Okay, so now I'm going to get back to these objects. There are many types of objects in R, many classes of objects. We have a single number, like you saw before, X and Y. It could be a number, it could be a character, the letter C. We have a vector, or a one-dimensional array of numbers, of characters, logical values like true and false, or factors. And factors are another important thing that we use in R. We also have matrices, so now we're getting into tables of numbers, or tables of characters. Okay, so we now have rows and columns, but a matrix all has to be of a single data type. So they all have to be numbers, or they all have to be characters, all have to be logical, and so on. That's not particularly useful for us. What is useful is this, and this is the most important type of data structure in R, the data frame. It is a matrix-like object where the columns, which represent variables, are allowed to be of different types. So one column might be a factor, another column might be number, another column might be logical, and so on. And that's a data set, in other words. Other types of objects are lists, and data frames are really just an example of a list. And technically functions, analyses, all of these things are example of objects. A very good convention in R is when you have an object, always put the object type in the name. So if I have a matrix, which represents my data, I'm going to call that object mydata.mat, because I just need to look at the name to know what type of object that is. If it was a data frame, I might call it mydata.df. Okay? It's a very good idea to do it. You don't have to, but it will save a lot of pain later on. So mydata.df would be a data frame. Just some very quick conventions on naming. We can use letters, numbers, periods, and so on. And if we want to assign a value or values to an object, we can use this arrow, which is a less than sign followed by a dash. So if I want to put the value of 7 into the object myval, I put my.val, and I'm going to assign 7 to that. Note, I could also use the equal sign to do that if I wanted to, and sometimes I do. But mainly I use this arrow looking, well, it's really 2 characters. I would avoid underscores in names. I believe R can deal with them now, but in earlier versions of R, an underscore meant the same thing as the arrow did, which was a very bad choice on the original developers on R, to make it to use an underscore for assignment. But I think they've solved that now, but I would avoid underscores anyway. I don't use them anywhere in R. Also note, if you literally mean equals to in R, we use the double equal sign. So if x equals 7, do this, I would use a double equal sign. That's the same, by the way, as C and C++ and Java and those types of programming languages. They do much the same thing. So now let's talk about data frames. They are the most important data structure. And it's the most commonly used data structure. They're really our data set. That's what it is. So data frame is just the R word for data set. A matrix-like object, again, where the columns can be of different types. Some can be numbers, some can be strings, some can be characters, single characters, and so on. So how do we get our data into a data frame? Well, rarely are we going to manually enter this data. That would be crazy, because a lot of the time we have hundreds of observations and we'll have 20 or 30 variables. We're not just going to manually enter it in. Most of the time, we're going to actually enter it in via a data file. So let's just consider an example here. Very simple data set containing 200 patients on which the following variables were measured: patient ID, age, systolic blood pressure, diastolic blood pressure, cholesterol, their socioeconomic status, which is a factor variable. I think there's 5 classes, and BMI in its numerical form, so not BMI class. And I have stored these in a comma-delimited text file. So a text file where commas separate the values. CSV, comma-separated values. And if I want to read this data in, how would I do that? So the data will look something like that. That's just an Excel. There's two ways of doing it. Actually, there's about 1 million ways of doing it. And different textbooks will show you different things, but I always just read things in with CSV. It's much, much easier than getting into the much more generic functions. I can put both the directory and the file name and do it all in a single command. So, into a data frame called mycol.df, I'm going to read a CSV file. So this is a function, and there is my CSV file right there. Now just note, and this is a common mistake, that the / is used in R, not the \. The \ means something else in R. So we can't use it for directory structures. Actually, your way. I'll do it your way for you. So note that / is used. Alternatively, you could use a double \. I just use the / particularly because I'm a Mac user and it uses / anyway. I don't actually do this this way. What I do is I will split this up into 2 different steps. I set my working directory where my data is, where I want to read data from and send data to. And I will set that up first. So set working directory. Sorry, I've changed the drive level there. So D, intro to R, basics, and then I will read my data in. So mycol.df, read cholesterol.csv. Okay, so that's how I do it. And that's an important command. Okay, because you're almost always going to use that. We can also read in data from other stats packages, including SAS, Stata, the other one I mentioned, using the foreign library. In other words, read data in from a foreign package. I will have to tell R that I want to use the foreign package. So at the top of my syntax file, I will write library foreign. Give me access to the functions available in this library. Set my working directory. This time, I'm going to read a .dta file. In other words, a Stata data file. So mycol.dta.df is read.dta, and that's my data stored in a Stata data file. Okay? I try to avoid reading things in from other packages. A lot of the time what I'll do is just go into that package, if I have it, and then just export the data back into a text file. It's okay for most situations, but I have noticed with specific types of data sets, in particular survival analysis data sets, where strange variables are created by packages, they have their own ways of doing things, that strange things can happen. So I particularly avoid doing this when I'm working with survival data or time to event data. Yep.
When you save that cholesterol.dta on your PC or whatever the laptop, you have to specify the path for the file.
The path, that's exactly right. So I've just saved that DTA file into my directory called intro R basics. So I'm telling it to look there. In fact, when I set my working directory, I'm saying look there for everything, not just this data file. Okay, if I was just going to use this directory once, I might do something like this. But by setting the working directory, you're saying, here's the directory I'm going to do all my work from. Okay, I'm going to read data to it, I'm going to print files out to it, or save files to it, and so on. So it just means I don't have to write that big string of characters. And one thing, whenever you're programming, when you have big strings of characters, you make mistakes all the time. You spell things wrong and so on. So I like to avoid doing that. One thing I have done for you is I've actually provided you a data file that we're not actually going to use for our analysis today, but I've given you a CSV file called autism just to practice reading data into today. That's one thing we're not going to bother doing, except for that one thing. We won't even use that data in that form. Also just note that there can be a problem with value labels, like SPSS likes to put, which is a nice feature of SPS. Yes, there are some nice things about SPSS. That it actually puts labels on its values. It's got a nice way of doing it. I know Stata does it too. But it can cause problems when you're switching data between different stats packages. That should I use the numerical codes or should I use the value labels associated with it? That can just be a little bit of a pain. So again, it's something I tend not to do unless it's a simple little data set. I tend not to read data in from Stata or from SPSS. I export it to a CSV file using those packages first. Okay, so now I'm just going to comment briefly on libraries. There's two types of libraries in R. There's ones that come with R when you download it. And there's ones that people like me or you have written that we have to actually go searching for to download them specifically. But regardless of whether they're a third-party library or they're one written by the R core team, we still need to tell R to put it into memory. Now I'll throw this question to the floor. Why do you think R doesn't just load everything into memory when you start it? That's exactly right. That's exactly right. R has thousands and thousands of libraries, okay? If it loaded every library it has into memory when you started up R, it would probably leave a tiny little bit. You'd probably add two numbers together because that's all the room you would have left in memory, basically. So like C, C++, Java, those types of programming language, it actually says to you, if you need it, tell me, okay? I didn't bring my kitchen sink with me today for this lecture, just in case I wanted to wash up my cup. If I need a kitchen sink, I will go and find a kitchen sink. Okay, it's exactly the same idea. R, when you start it up, gives you the absolute basics. If you want something specific, tell it you need it. Okay, and I do that, I've done that already by saying, I'm going to want to read in a foreign data set. So give me access to library foreign. Okay? It's a very smart way of keeping R as efficient and quick running as possible. So it makes a lot of sense. Okay, so as I said, there's two types of libraries. The ones that you automatically get when you download R, they're not in memory, but you still get it with R. Foreign is an example of that. When you download R, foreign comes with it. But if you want to access its functions, you have to tell R. The others is the third-party library, and we use two examples today of third-party libraries. LME4 for linear mixed models, and GEEPAC, which is for generalized estimated equations. We are actually going to have to go and download those packages. The good news is you only have to download them once. Once they're on your computer, that's it. You still need to tell R you want to access them, but once they're on your computer, you don't need to go and download them again. Well, at least until the new version of R comes out. So, as I said, some libraries come with R, but still needed to be loaded into memory. Others need to be downloaded from the repositories. The most common repository you will go to, and very few of you will go to repositories other than this, is CRAN, which is the standard R repository. Okay, and it will, you'll see later this afternoon, it has thousands. There are thousands of libraries available. The only other repository to note is if you work in the genomics area. Does anyone do microarray analysis or any high throughput stuff? Yep, okay. You may have heard of Bioconductor. Have you ever heard of that? Bioconductor is a repository especially for those types of studies. And there's thousands of libraries and data sets there. Okay. Okay, so as I said, an example of that is LME4. I'll show you how to do that today. Okay, so just to come back to this, to remind you, there are two things we need to understand about libraries. First, installing a library. Installing a library means getting it off the internet, okay? So LME4 does not come with R. We're going to need to put it on the machine. That's called installing it. The second step is loading it. So putting it into memory, making those functions and data available to R. So just notice the difference between these two things. We only need to install something once. To load it into memory, we have to do that every session. But if I write that right there at the top of my syntax file, that means load it into memory. Okay, so I don't have to literally type it myself every time. So just remember those two different aspects of libraries. Okay, so once I've got data into memory, how do I actually have a look at it? I can use syntax to do that, or I could just click that in RStudio. Okay, and again, I suppose the best way of showing you how to do this, no, I might run something very quickly. I'm just going to jump out for a sec of this. I'll just get RStudio. What have I got here? Okay, I'm just going to clear my memory out. Okay, so here I am just going to load some data into memory that is in a CSV file. If I want to look at what is in that file, which is in that data, I can just click this. It's the easiest way of looking at data, and there I go. It opens a spreadsheet-like object up, and I can actually look at the data. There's the variable names, there's the row names, and so on. Okay, you'll get practice at doing that later on this afternoon. Okay, a very, very strong feature of R is how we can access and subset our data sets. It's got a very smart way of actually doing it. One thing I can do, and I'm not going to show you how powerful this is because I would have to go into quite a bit of detail. But basically, whenever I have a matrix or a data frame, to access a specific row or specific column, I use these square brackets. So if I wanted the first 10 rows, for example, I could say, give me rows 1 to 10, or the first 10 columns, I could say, give me columns 1 to 10. If we leave out this row reference, type nothing in other words, so there'd just be a comma there, and then I would have column reference, it will give me all rows by default, and vice versa with the columns. Okay, so let me give you an example. If I write mydata.df, comma, so there's nothing before the comma, means give me all rows, because I haven't given you a subset of rows, so by default give me all rows. So there should be something there if you want a subset. So this is only going to give me columns 1, 3, and 5, but it will give me all observations. By the way, the C just means combine or concatenate. So just combine these three numbers together. It is a pity I don't have more time because I would really like to show you how powerful this feature is. It's an incredibly powerful feature. And I mean, you're looking at it and you're going, so what? But you can subset based on this data frame, on other data frames. It's a way essentially of querying your own data frames. It's very, very powerful. The other thing to note, and I'm sure I'm not the first person to tell you this, but when writing syntax, it's very, very important to document it. Because if you write something, you will come back 2 weeks later and you will say to yourself, what was I even thinking when I wrote that? I have no idea what this code does. Worse, if you give this syntax to someone else, they're going to have no idea of what the syntax does. So we can use the hash symbol to write our comments. I can write anything here, blah, 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 blah. Okay? R won't see that. It sees the hash symbol and just ignores that line. So, for example, set my working directory, set WD, yada, yada, yada. Read in a comma delimited cholesterol, read in the comma delimited cholesterol data, mycol.df. So it's a very, very good habit. And I'm sure you do this already with your data file, or who doesn't? Who just thinks that when they come back to their analysis in 3 years, they will remember exactly what they meant. I don't even remember for 3 days. I don't know what that means. Okay, so documenting your code has 2 major advantages. You and other people can understand what you've done. And if you do a very good job, it is a copy and paste methods section, isn't it? So your statistical analysis section for your methods can actually be written into your syntax. And when you do detailed analysis, that's a very, very good idea. Because if I don't do that, I won't remember every little step I did for standardizing the data or for all of these different things. So if I document it very well, I can actually write my method section, or at least certain sections of my method section, using my documentation. Okay, we're nearly there. R is very strong in its plots. There are thousands. Look, I've said hundreds. There's actually thousands available. There's hundreds available in R itself and thousands available on the internet. There are websites. The R Gallery is a very well-known one that have specialized graphs, and some of them look absolutely beautiful. They really do. So how would I create a plot in R? Let's look at the simplest possible plot, a histogram. So I will say, give me a histogram, and I'm going to get a particular variable from my cholesterol.df. What is the variable? It's the cholesterol level. Okay, so I want a histogram of cholesterol that is contained in the mycholesterol.df. Now, what's the advantage of this mycol.df $? I can have 20, 30, 50 data sets open at once. And I can tell it, I want this variable from this data set. I know most other packages, yes, they allow you to have multiple data sets open, but it's rather painful to do that, to have all of these different data sets. R makes it very, very simple to have multiple data sets open at once. Okay, so just remember this mycol.df $. It's actually a very important feature. It just means cholesterol from mycol.df, or contained in. So this will give me a very basic histogram. It gives me the default title on it, the default x-axis, the default y-axis, no colors or anything. So just, I'll get you to look at that. So I didn't tell it to do anything except give me the plain generic brand histogram. What about if I want to put some more features on it? I might want to use my own heading for it. So the main heading, my first histogram. I might want to give it my own X label, cholesterol. I might want to use a different colour, C equals red. Okay? So just note the difference between those two statements. Okay? Note that when I want to use the default, I don't have to specify anything. It just uses the defaults itself. So the default colour here was white. The default heading was histogram of the variable name. And the variable name was the default x-axis. So I can actually tell it that I want to tailor-make this histogram by giving it more features. The only thing you have to put in is this, but to make it more my own, I can tell it to do other things that aren't the default. And there's usually, with graphics in particular, there's 30 or 40 or 50 parameters you can actually change. If you don't change them, it gives you the default. Okay, let's do the same thing with a box plot. Now just note, all I need to include for a box plot is the variable. But I want more than that. I want to give it my own heading and my own Y label. So I specified those. So by box plot, the data to use, and what the main heading is, and what the Y-axis heading is. Dealing with categorical data, just looking at a frequency table, I just literally write table. That's it. So there's mycol.df $sign BMI class. Okay, and that shows me 2 people were underweight, 93 were normal, 105 in the overweight obese class. Just note, there's also things like proportion tables and things like that available too. So if I wanted the actual percentages, I could have got those in that way. I'm not going to go into these basic things in much detail. There's a lot of material available on the internet. There's many free textbooks available and wiki books that you can look at to get all of these sorts of things. I'll talk about that in a minute. I've actually got probably about 10 free textbooks with me if anyone is interested that I'm happy to provide, or at least really what I would do is just Google search free textbooks in R and lots of them come up. Okay, bivariate relationships, just to remind you, what type of graph we have depends on our data type. So if I have 2 continuous variables, I'm probably going to look at a scatter plot. If my outcome's continuous and I have a categorical predictor, probably a side-by-side box plot. If it's 2 categoricals, I'd probably use a cross tabulation. So a side-by-side box plot, my Y variable, squiggly line, tilde, BMI class. Just note, this format is very important for modelling. You're going to see this about 10 times today. Y tilde X. Okay? That's a formula. So when we specify our models, we're going to do exactly that. Okay, so by the way, I just note, if you're using a Thai keyboard, many of them have the symbol on the keyboard, but it won't type it out. I don't know why. So, and this is horrible, this is a horrible workaround. You might have to find a document or something on the internet that contains that tilde and copy and paste it somewhere, which is horrible. Or just go to a previous R file you've got and actually copy and paste. In other words, that character is not associated with your keyboard. I never remember how to do it. You could probably set it up as a hotkey or a shortcut key on your keyboard to do that. I'm not sure if the keyboards here will have that symbol. They have it written on here, but I've noticed whenever I've had a Thai keyboard, it doesn't do anything. I just hit it and nothing happens. Okay, So this will, again, all I need to put in is this first statement here. Actually I do need two here. I need to tell it where to look for the data. So both cholesterol and BMI class come from mycholesterol.df, but I don't need any of these. The main heading, the Y label, the X label. So it's rather straightforward. And I don't want you to necessarily remember these. Just come back and look at them when you need them, because it's not really what I'm here to cover today. I'm not here to teach you. But I want you to have the basics, so hopefully it means a little bit to you this afternoon when we get to the modelling. So scatter plots, here's an absolute basic one. X, Y, where to get the data, and that's exactly the same but with a little bit more detail. Just note a couple of things, and this is for all functions. R doesn't care what order you specify parameters in any function, providing you label them. So X equals age, Y equals cholesterol, data equals mychol.df. Since I've told what each parameter is, I can put them in any order. But before, when I just put the data in itself, it was expecting the data to be in the first slot. Okay? So had I written X equals, I can put it in any order. If I don't tell it what parameter it is, I have to put it in that first slot. If you don't specify a parameter, R will use the default. Just note, in this case, only for scatter plots, that PCH stands for plot character, so circle, triangle, star, so on. And by using data equals mychol.df, I don't have to prefix every variable with chol.df. Okay, just makes life a little bit easier. So that's going to provide that scatter plot. No, I'm talking about the second one here. Cross tabulation, really, I'm just going to put both variables in. It's still the table command, very, very simple. Okay, so it's going to give me a cross tabulation. Okay, so now we're getting to, I'm nearly there. I'm just going to talk very briefly about modelling. And I want you to pay close attention to what I'm talking about here, because we're going to be using this today. We're not going to be messing around with graphs. We're going to read some data in, and we're going to model that data. That's what I want you to understand today. As I mentioned before, the non-model based methods, t-test, chi-square, that there's not a consistent thread running through them, so they look quite different. But with the models, we do have that thread, unifying theory, running through. All of them have an outcome variable, all of them have predictors, so it's going to be y tilde predict and x's. Okay, so they'll all have that form. So the modelling in R is very intuitive. Once you understand it for one method, so for example linear regression or the general linear model, it's very easy to extend to the other models. It really looks exactly the same. I'm going to cover here this morning two methods very, very quickly, just with the modelling. The first is the general linear model, and the second is the generalised linear model, and specifically I'll focus on binary logistic regression. Okay, very quickly, this is not a lesson in linear regression or the general linear model, but remember a general linear model takes this form where y is a vector of observations of the outcome variable, which is generally continuous, and x is a matrix containing explanatory variables, and just note that these explanatory variables can be continuous or they can be categorical variables. So dummy variables which code to represent a categorical variable. Okay? I assume everyone's familiar with the general linear model. What's the difference between a linear regression and a general linear model? You could argue they're not different. What's a general linear model? It's a linear regression that can have both continuous and categorical predictors. That's all it is. It's really, us statisticians are the only people who actually bother making that distinction. Many people call a general linear model, they just call it linear regression. It has dummy variables, in other words. A general linear model will have dummy variables that represent a categorical variable. That's it. Okay, and finally we have a vector of parameters that relate X to the outcome Y. So to fit a linear model in R, and I should say the general linear model, sorry, that hasn't come out. There's supposed to be a tilde there. I don't know why that hasn't. I'll have to make that correction, sorry. I'm just going to make a note of it. So between that Y and X there should be the tilde. A little symbol. Okay. It is a simple matter of my.lm, so my linear model. What type of object is my? It's a linear model. There's the arrow, linear model Y, which is my outcome variable, tilde X, comma, data equals my data.df. Very, very simple. It's a Y variable, there's an X variable, there's a data set to look for these two variables. Now that will fit the model. That's all. It won't print anything out. In order to get the information that I normally want from a linear model, I need to tell it I want a summary. Now the summary will give me the betas, and it will give me the overall model significance at R squared. To actually look at the omnibus tests associated with multiple category variables, so for example BMI class, which might have 3 classes, I can't just look at the individual betas. That gives me the significance of the overall, the individual levels. Remember, I have to do a global test before I can do local tests for any multiple category variable. So I need to run an ANOVA statement as well, and that will give me those omnibus tests. So are any of the BMI groups different from each other? Yes. If they are, I can then go for betas and find out which one's different. But remember, we have to do global tests before local tests. Okay, that's all I'm going to say about the general linear model. Again, this isn't why I'm here today to discuss this. I'm here for the longitudinal model. So I'm assuming that you're quite familiar with the general linear model and the generalized linear model. Now, I hope so, because it will make the longitudinal models much simpler for you. Okay, a generalized linear model is a model that can be represented in this form, where G is some link function that linearizes the YX relationship. Okay, and it needs to be monotonic and differentiable in order for maximum likelihood estimation to be possible. So what are the main differences? This should be a revision for you between the general linear model and the generalized linear model. The generalized linear model can be used to model outcomes from distributions other than the normal distribution, so binomial, multinomial, Poisson, etc. These distributions we see all the time in health studies. That's why the generalized linear model is very important. How do GLMs do this? They essentially get a general linear model and do a little bit more to it than that. They do this via a link function. That is, a function that linearizes the relationship between the y and the x's. And this is a fundamental difference between a general linear model and the generalized linear model, is the betas in a generalized linear model are estimated using maximum likelihood estimation as opposed to least squares estimation, which is used for the linear regression. In other words, least squares no longer works when you don't have a linear relationship between variables of a normal outcome variable. Okay, so what we're going to cover is the binary logistic regression. That is where we model the odds ratio using a linear function, and we take the log of the odds ratio. What's that link function called? The logit link, or logit link, depends on who you talk to. Okay, so that is essentially what a binary logistic regression is. And so basically we transform the odds ratio so a linear function adequately models it. So how do we do this? So the tilde has come out this time. How do we do this in R? So just to contrast it to the general linear model, here's the general linear model. My linear regression is a linear model, my y tilde x1 plus x2, and the data comes from mydata.df. For the logistic regression, notice we use the GLM. So it's not LM, it's generalized linear model. The formula looks exactly the same. The data statement looks exactly the same, but we have to tell it what type of outcome variable it is. By telling it that the y variable is binomial, I am telling it use logistic regression. Now, just out of interest, if I wanted to do a log linear analysis, in other words, a Poisson regression, so in other words, my y was a count variable, what should I do in that function? Family equals Poisson. That's right. That's all I have to do. Okay? There is a way of changing the link function to the non-default link, but I'm not even going to talk about that now as well. So I'm assuming we're going to use the canonical link. That is the link function that is most commonly used with that distribution. Exactly the same as linear regression or the general linear model, and this is the beautiful thing about R. Things don't change. They're really done exactly the same way. All models have betas. All models have some sort of ANOVA function for global tests, and so on. So if I want to look at the betas associated with my logistic regression, I just ask for the summary statement. It will give me the betas, which in a logistic regression represent what? The log odds. We don't like to interpret log odds. To do the global test, again, if I have a multi-category variable, I want to run this. But, and this is where R isn't so nice, is it's just going to give me the betas. I don't want the betas, I want the odds ratios. So in order to get it to print out the odds ratio, and I just wrote this function myself, in order to get the odds ratios and their 95% confidence intervals, I just run my model through this function, which is print odds ratios and confidence intervals. I've provided you that function, so you can do that yourself too. You'll see today where that function is. So just note that it's not standard in R. I wrote it. It's nothing hard. It just exponentiates things. So in other words, if you want those odds ratios and their confidence intervals, which is the typical way of reporting logistic regression, that you'll use that function. Okay, now what do? We've read in our data, we've generated some graphs, we've run some analysis. What do we do when we want to save all of that? There's two things we can do. We can just save our syntax file and rerun it again. Most of the time that works unless you're working on a very, very big data set and it's taken you an hour or two to do the analysis. So what you could do instead is save the workspace. That's saving your session. So if you work on a single data set, so for example in your PhD thesis or whatever, you've got one big data set that you do all of your work on and your analysis is done over months, you can just save your session and start off where you ended yesterday. Okay? So what I can do is save that session and then I can load that session into the workspace tomorrow. I've actually given you an R workspace for today that we're actually going to use. That's the longdata.rdata file that I've given you. So I have given you one and it can store data sets or data frames. It can store analyses, functions, whatever. So in the one I've given you, long data, there's 3 data sets, the ones we're going to use today. There's a set of functions, including this one here. I think there's about 4 or 5 functions that are provided for you, and that just makes life a little bit easier. To save a workspace, I could just use the save.image statement, and that will just save it into my working directory. So I'm going to call it la.rdata. To load it up, I just use the load statement. Alternatively, in RStudio, I could just, where was I before? I can just save the workspace here and load it in here. Okay, so I can just use these icons here in the workspace tab. It does exactly the same thing. Okay, last thing. I just want to talk a little bit about getting help, because when you're first starting, it's a very important thing to be able to do. And our help is not the easiest thing to deal with, particularly it's on-board help. So R is tricky when you first start. It is, there's no doubt about it. One of the ways to make it much, much easier is to be able to use the help well. So I'm going to talk about 3 main aspects of help. First, R comes with its own introductory textbook that you can just get from the help menu. Second, searching help, which I use very rarely, but I know some people who do use it a little bit. And the third is the HTML package help, which I use quite a bit, but it takes a little getting used to. You need to know where to find things and so on. So this is the one here that I use the most, but you'll probably start using that after using R for a week or 2. You don't start using that straight away. I'm also going to discuss resources on the internet that make starting R much, much easier, and there is so much out there now, and particularly the YouTube walkthroughs. They're very, very good. There's hundreds of them. So the free introductory text you get from R itself, not RStudio, and when you go to help, manuals in PDF, an introduction to R. So it's about 150 pages. You can just print it out. It gives you the absolute basics. I don't ever sort of refer to it anymore. There are other textbooks that I think are a little bit better, but it's a nice, gentle introductory text. To search help, I could just go to the menu, either in R or RStudio, and type in a keyword, or at the prompt I can just write help.search, for example, t-test. If I know the exact name of the function already, I could literally just write help t.test. I never use that because if I know the name of the function already, I know its library, so I just go to the HTML help. So I never use that myself. So the help I most commonly use are the HTML pages. So for example, in RStudio, I'm going to go over here to help. I'll just go home to the home, and I'm just going to go to packages. So for example, I'm just going to go to the base package that comes with R. It's one of its main packages, and there's all of the functions in the base library right there. So for example, I don't know, let's pick something out. Now, why don't I go to the stats one? That might be a little bit more useful. And when you download a library from CRAN or wherever, it will automatically put the help in here for you. What am I doing here? So stats. Okay, so for example, I might go to the ANOVA function in stats. I'll just increase the size so you can see that a little bit better. And it will just tell me what ANOVA is used for. So ANOVA expects an input object containing the results of some model. So it's going to be a linear model or a general linear model and so on. So it will also give me an example, usually at the end, which you can actually run that example, because there are data sets that come with R, and all of these examples just use the data sets that come with R, just to show you how they work. This probably isn't the best example because it doesn't give you too much detail. Okay, as I said, it takes you a little while to get used to using the HTML help, but eventually it's probably the best source of help that you'll have. Okay, being open source, many people have put a lot of time and a lot of resources on the internet, so they've put a lot of time into building these resources. There's a lot of wiki books and free textbooks. There's a very famous one called The R Book, and it's about that thick. It's like a Bible. Okay, it's about 1,300 pages or 1,300 pages long. It's not so much a biostatistics book. A lot of it's useful, but a lot of it's in other areas as well. But there's lots of books available, freely available for R. Because again, it's got this open source philosophy. I remember with SAS, there's the big SAS manuals that when you buy SAS, which is $5,000 US for the yearly license, so it's prohibitively expensive. One of the things you did get for all of that money were these big manuals. Really, these are sort of like the same things, but everything's free. There's also a lot of websites that are especially for beginners or very well put together and very simple. There's a site called Quick R, which just shows you the absolute basics on how to do a particular analysis. It's very succinct, so that's a nice site. Lots of YouTube walkthroughs. How to do this, how to do that in R. There's also a good site called R Function of the Day. Probably a little bit more for the advanced user who has a little bit of time to develop their R in different directions, which may not be relevant on the day, but may turn out in 2 years to help you. So our function of the day will give you a very interesting function that you may not be using at the moment, may not be important to you, but one day you'll probably use it. Alternatively, when it comes to these walkthroughs, I would just go to YouTube and type in R for beginners or Introduction to R in YouTube's search engine. There's lots of stuff there. One thing I use a lot, and the more either advanced R users or people doing very specific things in R, I'll come across something and I go, oh, particularly with data stuff, not so much with analysis, but with data management, how to do some strange little manipulation. And I'll sit and think for half an hour about how I might do it. And I just think, I might just look on the internet and see if anyone's done that before. And you'll always find that 5 or 6 people have come across this problem before, and they'll give you a very nice, elegant way of actually doing it. So there's specialized pages that are dedicated to R and other open source applications, like Stack Overflow is one of them, where you'll find you don't have to reinvent the wheel, someone else has actually done it for you. So that's very useful, particularly if you've got a very specific problem to solve. Not, how do I do an ANOVA? They're not going to answer that question. Okay, so a final word. R is an extremely comprehensive package. It can do more than anything else by far because of this third-party contribution thing. SAS, Stata, definitely SPSS, they can't keep up with it. There are arguments against that. You could say, what about debugging and things like that? If I use something that's third-party, that's brand new, couldn't there be errors with it? That's a potential cost with something that's brand new. It's also a comparatively low-level language. In other words, as far as a specialised language goes, it's quite low level. You don't just write, do my analysis, and it does everything for you. You have to be quite specific. So if you're not used to any coding, now I assume most of you have been exposed to some sort of coding in Stata or SAS or whatever, so it shouldn't be too hard for you. But if you haven't ever done any coding before, you might have to get used to that, and really just the logical ways of putting a syntax file together. However, R is free, it's open source, extendable, and is one of the strongest and most versatile packages around. I shouldn't say one of, it is. As far as stat packages go, nothing else comes close for that reason of open source, third-party contributors. And for the statisticians out there, and I think particularly the methodologists out there, it's no doubt the package of choice. So if something is not off the shelf, and I hope you know what I mean, it's not a standard analysis, R is the way to go. If you just need to do linear regressions, or logistic regressions, and that's all you ever do, then maybe Stata and SAS are fine. Even other more advanced things, but it's off the shelf, it's a standard analysis. Those packages are fine, but if anything is a little bit left field, in other words, not standard, then R is by far a superior package. And I have found for most converts to R, once they've put in the initial hard work, they don't look back. So yeah, it's a little bit of a religion like that. You know, once you convert, there's no going back to the other ones. I mean, that doesn't mean I hate other stat packages. I still like Stata in particular. I think Stata is a very nice, succinct language. It's a very nice way of doing things. I don't think I'll ever go back to SAS unless I absolutely have to. And as I've mentioned before, I hate SPSS. Okay, so the number one hint for learning R is to use it, and use it a lot, and you will be like me and have no hair after the first couple of weeks. Mine hasn't grown back, by the way. You'll rip your hair out. But after you get used to it, it's wonderful. It's an absolutely wonderful and powerful package. One thing I did find particularly painful to start with, particularly with data input, with reading and data, is there's about 100 ways of reading data in, and different textbooks will tell you different ways of doing it. I always use read.csv. That's my only way. I only ever read data in that way. I might occasionally read in a Stata file, but different books will do it different ways. So if you look at 10 textbooks, it will give you 11 ways of actually doing something. So for data input, I always use read CSV, and I've stuck with that. You can use what you like, but what I would suggest is you pick one method and then you stick with it. Okay, that's it. Any questions? What's that, sorry?
It says the working library is disappear after you close the program. So if I wonder in the working space is still there or disappear after we turn
Okay, now with SAS you can save that working space if you want to, but that's what I was talking about before with workspaces. You can just let it disappear or you can save it. And that was that save.image command I gave. Or you can just use this here, which is to save. So if I save this now, it would save a workspace with temp.df, which is just data. But if I had an analysis in there as well, it would be temp.df, my linear model, so I can save that workspace using that. So just click that little disk there, or I can write save.image, whatever I want. So yes, I can save that workspace, or I can just save the syntax file, which you would do in SAS as well. So if it's a simple and quick analysis, why even say simple? If it's a quick analysis, I can not bother and save the workspace. Just save the syntax file, because that's just a shorthand way of saving that work, isn't it? I just run the syntax file. Or if it takes a little bit longer or it's a little bit more complicated, I can save the workspace, which is the result of that syntax file. Do you know what I mean? So the answer to that is yes, you can. You can save the workspace. You can save all the work you've done in two forms. One, the syntax, which is the recipe to get that, or number two, the product itself, which is the workspace. Does that make sense? Any other questions? Okay, I think you've been very good and you deserve a coffee. Is that right? Look at that, 2 minutes.
Yeah.
You're getting off 2 minutes early for good behaviour.
So let's keep coffee break fairly short, maybe 10 minutes because we've got a lot more to do today.